In this example, I'm going to show how to graph a rational function by hand by finding all the important parts and characteristics and working our way through that. So in this particular case, we'll start by looking at the function m and doing some factoring on the numerator just to see if we get any common factors to check to see if the graph will have any holes in it. So this would factor to x minus 1 times x plus 1 all over x plus 2. So the conclusion we can make from here is that there are no common factors to the numerator and denominator. Therefore, the graph will have no holes. No holes. From here, we can move on to other important characteristics. We can look at the vertical asymptotes. The vertical asymptotes will occur at the zeros of the denominator. So we want to see where x plus 2 equals 0, which means x equals negative 2 will be our single vertical asymptote. For our horizontal asymptote, we see that the degree of the numerator is larger than the degree of the denominator. So there won't be a horizontal asymptote. But what I do note is that the degree of the numerator is exactly 1 larger than the degree of the denominator. So that means we're going to have a slant asymptote. So I've got to figure out what that slant asymptote is. In this particular case, since the denominator is linear, I will be able to use synthetic division to figure out the quotient, remembering that our technique is to figure out what the quotient of these two, what our numerator and denominator are. So for our slant asymptote, for our oblique asymptote, depending on your language, oblique asymptote, I'm going to use synthetic division, negative 2, because that's the 0 of the denominator. And I'm going to have a 1, negative 3, and a negative 4. Use my synthetic division technique. And I get a 6 there. So that tells me I have a quotient of this division of x minus 5 and a remainder of 6. Now, that x minus 5, that is what is going to be our oblique asymptote. In this particular case, it was pretty easy because I had a quadratic numerator and a linear denominator, so I could use synthetic division. Had the denominator been anything but a linear, I quite possibly would have had to use polynomial long division to determine that. All right? So I've got no holes. I got my vertical asymptote. I've got my horizontal asymptote. So I can probably start doing a little bit of graphing. So I'm going to go to my graph here. I'm going to put a scale on here. I'm going to choose to scale this way. I think that will spread it out well, give me enough space to work with, and have it be somewhat reasonable. Like we said, my vertical asymptote is at negative 2. I have no horizontal asymptote. My oblique asymptote was at, let's review here, x minus 5. So a y-intercept of negative 5 with a slope of 1. So that might be a little tough here. Maybe I didn't scale this perfectly great. We'll see if we can make do. We might have to extend a little bit here. So there's negative 5 with a slope of 1. Kind of work my way across here. Make a dashed line. I'm just going to cheat a little bit here and extend this. Oops, we want that black. Just to match. All right, so that's not a bad start. What I don't know is where the graph is going to exist quite yet because I don't have enough information. I've kind of created 4 regions on the plane at the intersection of these asymptotes. I kind of figure that out. And easy way to figure that out would be to work with the x and y intercepts. So I'm going to go with the x and y intercepts as a start to maybe getting some information there. So the y-intercept is probably easier because that's just evaluating the function at x equals 0. So I had 0 squared minus 0, minus 3 times 0 minus 4 over 0 plus 2. And as usual, we just end up with the ratio of the constants. So I have a y-intercept at negative 2. So I can go back to my graph. I can plot a y-intercept of negative 2. That helps. I know graph is going to exist in that piece of the graph. For my x-intercept, let's just kind of get you out of the way there. Just put you over here. For the x-intercept, I need to set y equal to 0. And that can be a little more troublesome at times. So 0 equals x squared minus 3x minus 4 over x plus 2. And depending on your approach, you can either multiply both sides by x plus 2 or just realize that the only way a fraction has a value of 0 is for the numerator to have a value of 0. We've seen the factoring of this. So I get x equals 4 and x equals negative 1. So we see 2 x-intercepts, an x-intercept at 4 and an x-intercept at negative 1. Back to my graph, an x-intercept at 4, an x-intercept at negative 1. So those 3 points indicate to me my graph will look like this in that particular quadrant. So that tells me a little more information. That tells me my graph will not exist here because I would fail the vertical line test and I would not have a function. So I can say that. Furthermore, it tells me my graph will not exist here because if my graph did exist here, it would have to look something like this. But that would create an x-intercept that I didn't find when I went through the process of finding the x-intercept. So by elimination, the rest of my graph must exist down here. And I did not choose a great scale for my axes because I did not get my asymptotes in there very well. And you should be able to confirm this by graphing using a graphing utility on your calculator or Desmos or something like that. All right, so here's an example of graphing a rational function that had a slant asymptote.